Imagine trying to build an entire universe right inside your computer. I mean, it sounds completely impossible, right? And for a long, long time, it pretty much was. But today, we're going to look at a brilliant scientific hack that's actually making it possible. And the solution isn't a bigger supercomputer, it's just a way, way smarter idea.
You know, cosmologists are trying to solve the ultimate puzzle. How did we get from that single point at the Big Bang to this? Well, this cosmic web filled with trillions and trillions of galaxies. Their best tool for the job is a computer simulation, basically a digital sandbox where they can test out their theories. But they've hit a wall, a very, very big wall.
I mean, think about it. The universe is just too vast. The amount of computational power you'd need is, well, it's literally astronomical. So what scientists have to do is simulate just a tiny cube of the cosmos and kind of hope that it's a good representation of the whole thing. But as we're about to see, that's an incredibly risky bet to make.
And this is where something called cosmic variance completely ruins the party. The best way to think about it is like a cosmic lottery. When you grab a small patch of the universe to study, you might get a perfectly average sample. Or you might just happen to grab a patch that's unusually crowded with matter, or maybe one that's strangely empty. This statistical noise makes getting reliable results incredibly difficult.
So for decades, cosmologists were really stuck. They had to use a brute force approach, a method that was as inefficient as it was expensive, just to try and deal with this cosmic lottery problem.
And honestly, this brute force method is, well, it's a mess. The cosmic variance creates so much background noise. So if you're trying to study the effect of one specific high-density region, it's nearly impossible to isolate that one signal from everything else going on. It really is like trying to hear a whisper in the middle of a hurricane.
But what if there was a better way? What if, instead of trying to simulate a bigger universe, you could just simulate a smarter one? Well, that's the aha moment a team of researchers led by Christian Wagner had, and it has completely changed the game.
Their idea was it was so revolutionary. They thought, what if you could take that one patch of space that you're actually interested in, you know, that extra dense region, and just treat it as its own self-contained little universe?
And this right here is the core of the breakthrough. The old way was like searching for a needle in a cosmic haystack. This new separate universe approach, it's like you get to simulate just the needle. It's direct, it's elegant, and it turns out it's incredibly powerful.
And the logic behind this is surprisingly simple and elegant. First, you pick your patch of interest. Then you basically fence it off mathematically from everything else. You declare it a new separate universe, and then you run your simulation on just that piece. It's so much smaller, faster, and gives you a much, much cleaner way to get the answers you need.
Okay, so how can you just declare a piece of our universe to be its own separate reality? This is where the real genius of the hack comes in. You can do it by slightly tweaking the fundamental rules of physics, but only inside that little patch.
This is where the magic happens. The researchers realize that adding more matter to a patch of space is mathematically the exact same thing as changing the geometry of space-time within that patch. So, a region that's denser than average behaves precisely like a separate little universe that has a positively curved space-time. They aren't just adding more stuff, they're changing the very fabric of their simulated reality. So the crucial point to get is this. They don't just stuff more digital matter into their simulation box. No, they change the fundamental parameters, things like the expansion rate and the curvature of space, to perfectly mimic the effect of having that extra matter. It's a brilliant and profoundly powerful equivalence.
So did this wild-sounding idea actually work? Oh yeah. The results were nothing short of spectacular. This new technique delivered answers with a level of accuracy that was, frankly, previously unthinkable. By running these small, super-focused simulations, the team was able to calculate the effects of density on cosmic structures with, get this, 1% precision. In a field where you're dealing with the entire cosmos, that level of accuracy is absolutely incredible.
And here's the most amazing part. They achieved this without needing a world-leading supercomputer running for months on end. As the original paper says, these stunning results came from a modest simulation volume. It just proves that a truly clever idea can be far more powerful than sheer brute force.
And look, this isn't just some clever thought experiment. This is a validated peer-reviewed technique published by the prestigious Royal Astronomical Society. The separate universe simulation is now a powerful new tool in the hands of cosmologists everywhere. So let's zoom out for a second. Why is this more than just a neat technical trick?
because it provides a fundamentally new way for us to ask some of the biggest questions we have about our universe. This new lens lets scientists tackle some of the biggest mysteries in cosmology. Now they can cleanly study how galaxies form in different cosmic environments, they can better understand the elusive nature of dark matter halos, and they can test the very foundations of our cosmic model with a precision we've never had before.
The real power here, the one thing to remember, is isolation. By removing all that background noise from the rest of the universe, this method lets scientists see the pure, unadulterated effect of density itself. It's the difference between listening to a full orchestra and being able to hear a single, perfect violin note.
And you know what the best part is? This revolutionary idea doesn't even require revolutionary new software. It can be implemented using standard n-body codes. These are the very programs cosmologists have already been using for years to model that gravitational dance of countless particles. This makes the technique accessible to researchers all over the world, really democratizing the study of the cosmos.
So, the separate universe hack has given us a sharper, cleaner, and way more efficient lens to view our cosmos. The real question now is, what are we going to see? Will we finally unravel the mysteries of dark matter and dark energy? Or maybe, just maybe, will we discover something even more profound about the very nature of our reality?